Today we are going to start the earth science part, and we will start with the first section in chapter 25, the plate tectonics theory. نظرية الصفائح التكتونية, plate tectonics theory. This theory, it mentions the motion of the continents in the earth. This theory started by some hypotheses. The first one to claim it was Alfred Wegener. Alfred Wegener, he was a geologist and a scientist. He made a hypothesis in 1915 about the motion of the continents. He called it the continental drift, الانجراف القاري. He said the Earth's continents, they were once part of one large supercontinent. All the continents, all the 7 continents that we live on and we see on the Earth right now, once in the past, they were one big supercontinent. And he called this supercontinent Pangaea. Pangaea. So Pangaea was a big land, okay, including all the continents together. That was like around 200 or 250 million years ago. So this is the shape or the expected shape of Pangaea, which includes all the continents that we know right now. And for some reason, or for some kind of forces, this Pangaea, this supercontinent, separated into different pieces. And each piece moved in a certain direction on the Earth. Like this piece moved in this direction, this piece moved like this, this piece moves down, this piece moves up, this piece moves to the east, and so on, until they form the current continents we live on right now. The 7 continents, like Africa, Asia, Europe, North America, South America, Australia, and the South Pole continent, which is called Antarctica. Antarctica is the South Pole continent. In the North Pole, there is no continent. There is no continent. It's a large ocean, the Arctic Ocean. So it's solid because it's frozen, but it's not a land. But in the south, it's a land. So the Antarctica is a land, normal land like the one we live on right now, but it's covered by layers and layers of ice. But in the old days, millions of years ago, it was a normal land. It was full of life. It was full of animals and trees and so on. So this is briefly the hypothesis of Alfred Wegener. The Pangaea was there millions of years ago and then separated into pieces which we can see right now. What are the evidences that Alfred Wegener has used to prove his hypothesis? Number one, the shapes of the continents. The shapes of the continents. He looked at the shapes of the continents and he tried to match them up like a puzzle. Number two, the fossils. Fossils al-ahafir. Al-ahafir. So fossils from animals, animal fossils or plant fossils, he tried to match them up from different places or from different continents. The rocks and the mountain ranges in different continents. This is the third one. So let's start one by one. The shapes of the continents. If we look at the shape of Africa, the northwest coast of Africa, this one, let's call it A, has the same shape as the east coast of North America. Okay, it has the same shape. So they can match up together. They can match each other. So this is the first one. And also the west coast of Africa. Let's call it B. It matches the east coast of South America. Also, he said, if we take the South America and match it to Africa like this, okay, and we look at both of them. Let's look at the southern part or the southern tip, which is this one. Okay, they can be matched to the Weddell Sea in the Antarctica. They can be matched to some place in the Antarctica, which is called the Weddell Sea. We can see it on the map. If we look at the west coast of Africa, here in this place, we can match it to the east coast of the United States or the North America in general. Okay. Also, the west coast of Africa can be matched to the east coastline of the South America here. And if we look at the south, he says if we take the tip of South Africa, this place, plus the tip of South America here, they can fit in this area, which is called the Weddell Sea. This is the Weddell Sea in the Antarctica. Okay, so he said maybe that means all of these places, they were one continuous land with this shape. Okay, so South America and Africa and North America, okay, and Asia, all of them were one piece together. So this is the first one, the shapes of the continents. Number two, the fossils. He uses the fossils of some very old massive animals that have lived on the earth before the dinosaurs. Like let's say 250 million years ago, before the age of dinosaurs, maybe before 250 million years. These massive animals are not able to fly, but they can walk. And he found the fossils of these animals in different places in different continents. So that means they have moved from a continent to the other by walking. So these lands, they were continuous land. It was a continuous big continent. And there was no ocean in between. And that's why these animals, they were able to move from one place to the other place. Like here, the Lystrosaurus and the Cyanognathes. Okay, these are some Latin names. I don't think we need to remember the names. Okay, but at least to know the fact. So he found different fossils in South America and in the middle of Africa. He found also some other fossils for some animals in Africa, in India, Antarctica, and also the plant fossils. There is a fossil of some plants like the fern. Fern is a kind of plant. They found some fossils of these plants saved inside the rocks in different places, in different continents. Like they found the fern in South America, in Africa, in India, in Antarctica, and in Australia. Okay, so this continuous trace, it made Alfred Wegener to think that all of these lands, they were a continuous land in the past. The third thing is the rocks. He took rock samples from different mountain ranges, سلاسل الجبال, mountain ranges. Like let's say he took some samples from mountain ranges in South America and in south of Africa, and he found that all of these rocks are the same. They have the same age and they have the same composition. So they were very, very similar. So he claimed that they belong to the same mountain range. So he said the two mountain ranges here in the past, they were one continuous mountain range. Okay. Also in the north here, the other mountain ranges found in the Scandinavian part, in the Greenland, in the east coast of America, and in the west part of Europe, and some islands in the middle in between. Okay, all of them, they have the same age, same composition. So he claimed that they belong to the same mountain range. In the past, he said it was a continuous mountain range, but it splitted to different parts. Okay, so these are the three evidences that Alfred Wegener used to prove his hypothesis, which we call it the continental drift. The problem with Alfred Wegener, he couldn't explain the reason for the continental drift. why there is a continental drift. He thought at the beginning of some forces coming from the rotation of the Earth, the gravitational field of the Sun and the Moon, the centrifugal force, قوة الطرد المركزي, the centrifugal force because of the spin of the Earth. But actually the physicists at his time, they responded to him that these forces are not enough to cause such motion. Okay, so it was denied idea. So he thought of another reason. He proposed that these continents, they were pushing through the sea floor. They were pushing through the sea floor. So for example, if we have a continent like this one, this is Africa, for example, and another continent like this one, let's say this is North America or South America, and in between there's the ocean or the sea or whatever. Okay, and this is the sea floor. Sea floor means قاع البحر أو قاع المحيط. Sea floor. So he proposes that these two continents, they are pushed away through the sea floor. So the sea floor, for some reason, pushes the two continents away from each other. That's his proposal. The geologists at his time, they argued that the sea floor can do that. The sea floor is too rigid to do that. Too rigid, صلب جدا. And if this happens, there will be cracks and fractures in the sea floor. And that cannot happen. That's what they said at his time. So they tried to decline the idea of Alfred Wegener. Alfred Wegener, he was lost in the North Pole in 1930, and he was considered dead by this time, and he could not prove his hypothesis. But later, after his death, new discoveries came and supported his idea about the seafloor. Okay, so after Alfred Wegener, another scientist came, which his name is Harry Hess. Harry Hess, he had a ship, and this ship had a sonar. You know, the sonar is a device that sends ultrasound waves to the bottom or to the sea floor, and then when it reflects back, it measures the time of the trip. Okay, we call it the time of flight. And using very simple equation, distance equals speed of the sound times time, it gives you the distance, which is the depth of the sea floor. Okay, so if this is the sea floor, this is the sea floor, and this is the water level. So the sonar sends waves and it reflects back, so it measures time and it can measure the distance, which is the height of the water level or the depth of the sea floor. Okay, Harry Hess, he used this technique. He used this technique to develop a three-dimensional map of the sea floor. He made a map for the sea floor. So he was able to see the structure of the sea floor, what's inside. And he found something very, very strange. He found that there are mountains under the water. And not a mountain or two mountains, it's a range of mountains, mountain ranges, extends for thousands of kilometers under the water. So he discovered the system of mountain ranges on the sea floor, and they are separated by valleys. So they are like a peak and another peak, and between the two peaks there is a valley. That's a valley, that's a peak, and that's another peak, and in between there is a valley. Okay, and this issue extends for very, very large distance. He called this discovery the mid-ocean ridge. Mid-ocean ridge. Mid means middle. Ocean محيط, and ridge سلسلة جبال. So that's the mid-ocean ridge, the mountain ranges in the middle of the ocean. For example, he discovered one in the middle of the Atlantic Ocean. It's called Mid-Atlantic Ridge. The Mid-Atlantic Ridge is an example for the mid-ocean ridge. Okay, and it's found in different oceans on the earth. Okay, and you can see it if you use the Google Earth. You can notice this discovery here. If you look at the center, okay, of the ocean, you can find it here. This is the mid-ocean ridge of the Atlantic Ocean. You can see it here exactly in the middle of the Atlantic Ocean. So how these mountains were built on the seafloor? Harry Hess, he suggested that because of the magma inside the earth under the crust is buoyant. Buoyant means it has low density, so it can move up. It rises upward through some cracks in the crust. It rises upward through some cracks in the crust, causing the crust to spread apart. Let's see what does it mean. Let's say this is the seafloor. Seafloor. And this is the water level. Under the crust, this is also called the crust of the ocean, oceanic crust. Under the crust, there is the magma. What is the magma, guys? What's the meaning of magma? The magma is a previous stage of lava. The magma is some huge elastic rocks under the crust. They lie under very high temperature, so they are very hot, okay, and they lie under very high pressure. So because of the very high temperature and very high pressure, these rocks, they want to release the pressure. So they will look for any weak part to release the pressure. So they will go toward the crust. If there is a weak part in the crust, it will make a crack. It will make a crack in the crust. Okay? So it moves outside the crack, becomes lava, it turns into lava, and these lava are building these mountains. These lava are building the mountains. That's why he saw peaks, and between the peak there are valleys. Not only that, but because of the very high pressure, Harry Hess said that this pressure or these magma, they pushes the sea floor away from each other. So it causes the sea floor to spread apart. So what's going to happen is the sea floor is moving apart like this, and the magma will fill the new part by a new crust. So the magma will turn into lava, and this lava cools down, making a new layer of crust. Then the magma comes again in the weak part and make a new crack and pushes the sea floor away again, becomes like this. Let's try to draw it. This is the old part, and then the new part is pushed also. Then it will build a new layer again and again. Then after that, it will push it again more and more, and then it will fill it by a new layer, and so on. So this is a continuous, a new layer in the middle, and push it to spread it apart. Okay, so this is a continuous process. So Harry Hess said this is the reason for the spreading of the sea floor, اتساع قاع المحيط, okay, because of these magma and the high pressure under the crust. Okay, so a mid-ocean ridge forms as the sea floor spreads apart. So a new layer comes to fill these cracks and build a new crust. So guys, if we take, let's say I will take a layer or I will take a sample from the rocks at point A or at region A and at region B and at region C and at region D. Which one is the oldest rocks and which one is the youngest rock? What do you think? Yes, Ali.
D is the oldest and A is the newest.
That's right. So D is the oldest one because it's built very long time ago. And A is the youngest because it's recently built. Okay. So A is the younger and D is the oldest. What if we take samples? Let's take samples from different points, like let's say this place, this place, this place, and this one. Let's call them G, H, I, and J. What if we compare this one to this one? And we compare also this one to this one. And we compare this one to this one. And this region to this region. What do you think we will find? So the mid-ocean ridge is in the middle exactly. And we will compare different regions at a certain distance, like let's say I will go to 1,000 kilometers to the right and 1,000 kilometers to the left. And I will take a sample of the rocks from here and there. What do you think I will find? Similar to each other. That's right, Ali. We will find these rocks to be similar to each other. So why are they similar to each other? Because they were built at the same time in the same place. They were built, okay, at the same time in the same place. And they were built where? Where is the source? Here in the center, in the MOR. In these valleys, where the magma comes from. Okay? So the mid-ocean ridge forms as the sea floor spreads apart along narrow depression which called the Rift Valley. So the valleys in the middle are called the Rift Valley. Rift means شق أو صدع. Okay? So that's the Rift Valley. As it's called the Rift Valley, forms in between the peaks. So we will find the peaks coming from the lava, okay, and they are continuous. They are moving like this because the layer or the sea floor, it spreads. And in between, we will find this Rift Valley because of the magma and because of the cracks coming from it, or the magma coming from the cracks, okay. This process forms new oceanic crust. So the crust is renewable, okay, as lava fills this Rift Valley from below. So this was the hypothesis of the sea floor spreading, اتساع قاع المحيط, by Harry Hess. To prove this idea, they took samples of the rocks from different places in the ocean. They took samples of the rocks from the sea floor in different places in the ocean. Like, for example, they took some samples of the rocks from the west coast of Africa and the east coast of America. They drill in these areas. They took some samples. We call it the drill cores. Drill cores. These drill cores are very long columns of rocks. This is the bottom, for example, and this is the top of the core. When they take sample from region A, region A, which is the coastline of Africa and America, they found these rocks to be similar. These rocks are similar, meaning that the two places, they were adjacent to each other. Okay, they were adjacent to each other in the past. And also they found that at the bottom, the rocks were very old. The rocks were very old. And at the top, it's younger. So it was very old at the bottom and it's younger at the top. And when they determined the age of the rocks at the bottom, they found it around 4 billion years. 4 billion. And the billion is 1,000 million. So it's like 4,000 million years. Okay? So these are the continent, the oceanic samples near the continent, near the coastline of the continent. And when they examined the continental rocks in Africa or in America or Asia, they found that the oldest rocks, the oldest continental rocks on the earth has the age of 4 billion years also. So the oldest rocks on the earth has age 4 billion years, almost. So we consider the age of the earth to be around 4 billion years. Since the earth, when it cooled down and formed a solid layer or a solid crust, which is the continental crust, that was 4 billion years ago. So they found the age of these rocks at the bottom to be 4 billion years old, which is the oldest rocks. And when they move toward the MOR, and when they take samples, they found that these samples become younger and younger. So when they take samples very near to the mid-ocean ridge, they found these samples age to be very young, around or less than 200 million years. So the age of these samples near to the mid-ocean ridge, okay, is less than 200 million years. Okay? So this difference in ages can only be explained if rocks on the seafloor are continually being created in the mid-ocean ridge. It's created at the MOR in the center here. And then they move toward the continent. And also when they move toward the continent, they push the continents away. Okay? And they are being destroyed at another location. And we will study later in the next lecture, we will know why these layers, the oceanic crust, is being destroyed in another location. Okay? Let's first solve this problem. The problem here says the spreading rate along the mid-ocean ridge varies. It varies from an ocean to the other ocean. For example, in the Atlantic Ocean, the spreading rate average is about 2.5 centimeter every year. So the MOR produces a new layer pushing the seafloor, and on average, this has a rate 2.5 centimeter every year. Estimate how far in kilometers the Atlantic seafloor has spread over the past 100 million years. So in the last 100 million years, I want to see how long did it spread. So I need to find the distance if the time is 100 million years. We will use a very simple equation. Distance equals speed times time. Because here he says it's average. So we consider it a constant speed. 2.5 centimeter per year times time 100 million years. This gives us 250 million centimeter. So during the past 100 million years, the Atlantic sea floor has spread about 250 million centimeter. If we want to change it into meter, we divide over 100, convert it into meter, and to convert it into kilometer, we divide over 1,000. So we will remove 5 zeros. So it becomes 2500 kilometer, 2,500 kilometer. Okay, so this is how far the Atlantic sea floor has spread during the last or the past 100 million years. If we look in the map at the mid-Atlantic ridge, this one, the mid-Atlantic ridge in the middle, and I will try to measure the distance from the mid-Atlantic ridge to Africa, to a similar point in Africa, and to a similar point in America. If the two distances are the same, so this hypothesis also is right, because the idea here is what? The idea is the two continents at the beginning, they were here in the middle. They were adjacent to each other, متلاصقين. They were like one piece. And because of a certain force, the magma pushes them away from each other. So they started from the middle here. They started from the middle in this point. So I will try to take a certain point. For example, I will start from this point. And I will try to measure to a similar point to the right. That's almost around 3,000 kilometer, 3,100 kilometer to the eastern coast of Africa. And then let's take the same and do it to America. So that's almost the same. We said it's around 3,100 to Africa and almost 3,200 or it's 100, 200 something toward Africa, toward America. Let's take another point. Let's try to do it in another point. Let's take this point, for example. Measure it to the right here. This is around 2,500. And to the east, almost the same, 2,500. So we can consider it right, okay, that both continents, they started from the mid-ocean ridge. They were adjacent and they were continuous in the mid-ocean ridge, and they splitted apart from the mid-ocean ridge. One of them moved to the right of the mid-ocean ridge, the other moved to the left of the mid-ocean ridge. Okay, so it's almost right. They found else something very interesting. When they examined the regions to the right and to the left of the mid-ocean ridge, let's say to the right and to the left of the mid-Atlantic ridge, they found something very strange. They found what? They used a device called the magnetometer. They put it on the seafloor and they draw it on the seafloor to measure the magnetic polarity of the iron and some metals inside the crust or inside the rocks of the seafloor. As you know, when the magma turns into lava, the lava is a liquid. Lava is a hot liquid. And the lava contains different minerals. One of them is iron, nickel, and some other elements. And these materials or these metals, they are affected by the polarity or the magnetic polarity or the magnetic field of the earth. Like if you have a compass needle, if you have a compass, بوصلة, if you look at the needle of the compass, if you try to turn the compass right and left, the needle always directs to what? The needle of the compass to the north. To the north. Okay, so one part to the north, the other to the south. Always. Why? Because the magnetic field of the Earth in our age now, the magnetic field is between the north and the south. So in the past, 200 million years ago, when these lava came from under the ground, it has some iron. It has pieces of iron. These iron, they represent like the needle of the compass. So they take the same position of the magnetic field of the Earth. So the iron inside and the nickel and these elements that are affected by the magnetic fields inside the lava, they take the same orientation or the same direction of the magnetic field of the Earth. If the magnetic field is in this direction, so it takes the same direction. And when the lava cools down, what will happen? It turns into a solid rock. And what happened to the direction of the iron inside the rocks? These orientations or these directions become permanent. It becomes permanent. Permanent دائمة. Because now the rocks are solid and it saves the direction of the magnetic field inside the rocks. So if we look inside the rocks and measure the orientation and the polarity inside these rocks, it tells us what was the direction of the magnetic field of the Earth at this time, since the time of creation of this rock. So that's what they did. They used the magnetometer. This magnetometer on the sea floor, they draw it on the sea floor for several hundreds and thousands of kilometers, and they found something very strange. They found that the magnetic polarity in these rocks, they have different directions when they move from a region to another region. So in a certain region, for example, they find the magnetic polarity to direct to the south. And then when they move to another place, they find it directs to the north. And then when they move to another region, they found it again directs to the south. And then again to the north, again to the south. And when they move to another place, to the north. And if this is the mid-ocean ridge, MOR, when they go to the other side of the mid-ocean ridge, it's like a mirror. It's like a mirror exactly. They find the same change exactly. So let's say we will go, for example, 100 kilometers to the right and 100 kilometers to the left. We said these rocks, they have the same composition, the same orientation, and also the polarity of these metals inside the rock, they have the same polarity. If it is north, for example, the other one also on the other side, it directs to the same direction. Okay. If it is south, the other one on the other side directs to south. Okay. So this gives also an evidence that these rocks, they were created at the same time, okay, in the same place. And also the change in orientation, the change in direction of the polarity, in the magnetic polarity, it told us what? It told us that the magnetic field of the Earth has reversed many times in the previous time. It has reversed many times. Sometimes, for some thousands of years, it turns or it directs to the north. And after that, for some reason, it directs to the south. Okay? And after that, it directs again to the north, and then directs to the south, and so on. So that's what they found when they checked the magnetic polarity in the seafloor. Okay, guys? That's everything today. Thank you for coming to this lecture. Please, if you have a question, go ahead.